Hello everyone, welcome back to this series on light-matter interaction. After the two videos before in which we were exploring the semi-classical model of the light-matter interaction in which light was classical, now we are gonna also consider light to be quantum. Let's go to the full quantum model, in which matter is gonna be modelized as a two-level system, as a qubit, and light is gonna be also quantized. Let's jump right into it, and the model that we are gonna consider is the Jaynes Cummings model, which is the paradigmatic model in quantum optics and in quantum electrodynamics and in ultra-cold atoms and in atomic physics and all these fields of physics, that is used in order to do a very wide variety of experiments. For example, you can create, and we will derive that in the next lessons, non-classical states of light, Schrödinger cat states, Bell states, quantum correlations. You can start manipulating and having quantum control thanks to this light-matter interaction. And so let's see how this model comes about, and how can we solve it analytically. It's one of the few full quantum models in the interaction between light and matter that can be solved analytically, so it tells you a lot of insight about the physics that is happening. And I would say it's the most important model, clearly, in light matter. So let's go. So I would need two premises, two things that I'm gonna assume here. I'm gonna refresh a little bit the concept, but I'm gonna assume that we are all familiar with. The first one is the quantum harmonic oscillator. So when you have a Hamiltonian like the one that I'm writing here, that is quadratic in some position and momentum operators that I call here x or p. So that means that the energy is quadratic with this observable x. Then this is an harmonic oscillator, but the quantum mechanical version of it, because x and p are not position and momentum the functions, but rather they are quantum mechanical operators. And when you solve this model in quantum mechanics, which is a thing that is done in the courses during the bachelor's or the master's, one finds that the eigenvalues of this model are called the Fock states, or the number states, are these states here, n, with n is a natural number, and n is the number of bosonic modes, or the number of excitations, or in our case is the number of photons that we are considering. And so we have the vacuum state, which is this 0, and then we have the following Fock states, 1, 2, 3, etc. until infinity. And these green functions that I'm writing here is just the wave function as a function of x, so it is projected in the x operator subspace. And so it tells you the probability of finding the particle, the photon, at a certain location. So this is a concept in quantum mechanics that I'm going to assume we know. We need this because we are quantizing light, and light inside a cavity works like this. We are going to consider a single electromagnetic mode of light that is living in a certain cavity, a general cavity. So this is what I write here. When one has a cavity, one can write the Hamiltonian of this system. It's a single electromagnetic mode approximation in which the mode has a certain frequency. Omega is the frequency of the field, the same omega that we used in the semi-classical model as well, for the frequency of the classical field in that case. And then one has A daga A, where these A are the annihilation and creation operators of excitations in the system. In this case, is the creation or the annihilation of photons. So if I apply the annihilation operator on a number state, I get one less photon inside the system, and I get this value, square root n. And similar to when I apply the creation operator, I just create a photon on the system. So this operator A daga A is actually the number operator n, and it diagonalizes the Hamiltonian. So this Hamiltonian is diagonal in the number operator. And then we have also this factor of 1/2, which is the vacuum energy, is the energy that the cavity would have even if there is no photons inside the cavity, which is relevant for physics, and it's a consequence of the uncertainty principle, but that we will see that for us it will not play a role in what follows. Alright, but I'm assuming that we all know what is a quantum harmonic oscillator and what are these Fock states. Now the other thing I'm going to assume is that we are all familiar with the quantization of the electromagnetic field. Of course, these things, the quantum harmonic oscillator and the quantization of the electromagnetic field, could be lessons or could be videos about it in the future. They could become their own video and their own explanation for that. But for the time being, we are going to consider that we know. And in particular, what we called before the electric field function is a spatiotemporal function that fulfills the Maxwell's equation, but is a vectorial field. Now it has the category of a quantum mechanical operator, so the electric field operator. And the electric field operator in the context of a cavity single mode can be expressed in this way that I'm writing here. And this is what I'm assuming that everyone is rather familiar. You don't have to be super familiar with it, but you will understand better this lesson if you are familiar with these concepts. So this prefactor, square root h bar omega over 2 epsilon 0, this prefactor is the electric field that is created by a single photon, and then these functions f are the spatial solution to Maxwell's equation. So these are classical functions, classical vectorial functions that tells you how is the electric field in particular in that cavity. So there are certain solutions that depends on the cavity. And then we have exactly the annihilation and creation operators of photons, and here, as you can see, they depend on time. This is because I'm writing this electric field operator in the Heisenberg picture, where operators depend on time, and in the Schrödinger picture is the operators, they are time independent, and it's the wave function that depends on time. Okay, why I wrote it like this? Because probably you will see it in any quantum optics book written in this way, as with the time dependence. And this is because when you quantize the electromagnetic field, people usually works in the Heisenberg picture, because the equations and the mathematical formulation is easier to be carried on in this picture. But we will work actually in the Schrödinger picture, and so this temporal dependence, you will see it will just drop out because of the picture that we are working. Everything evidently is equivalent. Heisenberg picture, Schrödinger picture, interaction picture are equivalent pictures, are just ways of mathematically writing it in a more easy or not way. Alright, so with these two ingredients, now we can say, okay, what is our system? The system that we are going to consider is a qubit, so a two-level system with two states, ground state and excited state, and splitting given by the frequency omega naught, and then light. And light is going to be a confined mode of light in a cavity with certain quantized levels for the photons, which are these Fock levels n. And they are going to interact between them. You can think about it in this way, that we have two mirrors. It's a schematic way of seeing it. It doesn't have to be like this. And there are plenty of even solid state platforms that they behave exactly equivalently to this way of seeing it that I'm drawing right now. We have a wave, so we have inside the cavity a certain electromagnetic wave, so a light field, and here we have an atom place that has two levels, and this wave is interacting with the atom and vice versa, of course. Alright, so let's write the Hamiltonian of the system. The Hamiltonian of this system is naturally the Hamiltonian of the atom plus the Hamiltonian of the field, of light if you want, of the cavity, plus the Hamiltonian of the interaction between them. Okay. Now the Hamiltonian of the atom, we wrote it in the semi-classical model that we derived in the last videos, and it's gonna be h bar omega 0, omega naught, and then the projector onto the excited state. This is a way of writing this Hamiltonian, in which the zero energy is given for the ground state, while the h bar omega naught energy is given for the excited state. Then we have the Hamiltonian of the field, so it's a cavity. So since it's a cavity, I just wrote before the Hamiltonian of the corresponding quantum harmonic oscillator, which is equivalent to this cavity. And now we have the Hamiltonian of the interaction. And the Hamiltonian of the interaction we saw in the semi-classical model can be written as the atomic dipole moment, D, dot product with the electric field. And in the semi-classical model, this electric field was a classical function, so it was as I wrote it right here. But right now we know that in the quantized version, this is a quantum mechanical operator. Now, this factor of 1/2 is arbitrary in the sense that it's also an offset in energy. We can put the energy of the cavity to be 0 for the h bar omega divided by 2, and the physics of the system is not going to change because it's diagonal in the sense that, if you want, this part is h bar omega divided by 2 times the identity matrix. So it's not doing anything. So this means that we can get rid of it for the physics that we are going to derive. So we are going to forget about it. And now let's see how is the interaction. So the dipole moment, the operator, we saw also in the semi-classical model that we can always write it as a certain vector that is a bracket between the ground state and the excited states of the atom times sigma plus sigma dagger, where these sigmas are the lowering operators of the atom. So for example, sigma is the lowering operator, is Eg, and sigma dagger is called the raising operator. Why? Because if I apply sigma to the ground state, I got 0, and if I apply sigma to the excited state, I got the ground state, so it's going down in one excitation of the atom. And if I apply sigma dagger to the ground state, I get the excited state. So that's why it's called the raising operator. They work in the same manner as the annihilation operators for bosons, but only in 2 dimensions. So there is only 2 states, excited and ground. This we saw it in the semi-classical model before. And I just wrote before the electric field operator inside the cavity. So let's write the interaction Hamiltonian just by substituting what we know about D and what we know about E. And when we do that, what we get is the following. So we get minus this electric field created by a single atom, h bar omega over 2 epsilon 0. Then we got this sigma plus sigma dagger from the dipole. Then we got this number, DEG. VEG, this number is exactly this. I call this DEG vector. It's this bracket. And then this is dot product with the spatial profile of the electric field, A plus the complex conjugate, A dagger. As you can see here already, the annihilation operators, they don't depend on time because we are in the Schrödinger picture back again. Okay, so this is the interaction Hamiltonian. And now what we do is we define a new variable, a new function that is called g of r, that has units of frequency. So h bar g is energy, it's going to be the interaction energy. And we literally can define it as the square root of h bar omega over 2 epsilon 0 with a sign, negative sign, sorry for that. And then the dipole bracket Eg dot product with the spatial function of the light field. And defined in this way, this G is called the coupling constant. So the coupling constant is gonna, as you can see, is not actually a constant, but it will become a constant in a few minutes, and it's gonna tell us about the strength of the light matter interaction. And 2G, just for the sake of being complete, 2G is called the one photon Rabi frequency. So if you remember from the semi-classical model, we defined what was the Rabi frequency, and here this is called the one photon Rabi frequency in the quantized model, and the reason for that will become evident in the following. And so first of all, G is in general a complex valued function, but it depends, its complexity in the terms of why it's complex depends on the phase of this dipole moment. But we can choose, we have freedom in choosing this phase depending on your specific system, but you can always choose it such that G is real. So the first thing we will say, and we are not losing generality here, is that G of R is real evaluated at the position of the atom. So this means that the Hamiltonian of the interaction with this G, it can be simply written as H bar G of R, and now sigma plus sigma dagger A plus A dagger. And now, as you can see, the interaction Hamiltonian reduced significantly, but it reduced because all the complexity or all the details about the specific cavity and the specific atom that you are using is encapsulated in the coupling constant. And that's why now we can write it in a very compact form. But it's the same general, we didn't do an approximation until now. But now we will do an approximation, and the approximation we will make is called the rotating wave approximation, and we did it already, and we explained it already for the semi-classical model. But the main idea here is that from all the products that you can see here, between the sigma and the annihilation and creation operators of photons, we will have one term that is going to be sigma A, another term that is going to be sigma dagger A dagger. But these two terms, if we go to the Schrödinger picture and we calculate the mean value of them, sigma A, in the unperturbed system, we see that this goes as e to the I omega plus omega 0 t. This we did it again in the videos from the semi-classical model, and this is the same with a plus or a minus sign. So these terms, they oscillate very rapidly, and their mean value is 0. This means that the dynamics of these terms is important at time scales of 1 divided by omega plus omega 0, which is typically a very small scale, time scale, and the average value over longer times is gonna reduce to 0. So the rotating wave approximation consists in replacing these terms, the operators, so let's say the operators, by their mean values over that time. But this mean value is 0. So typically what you say is that the rotating wave approximation discards these terms. And these two terms, they are called the counter-rotating terms. And this, again, we discussed it already in the semi-classical model. Counter-rotating terms. Counter-rotating terms. It doesn't matter. Okay. So the rotating wave approximation consists in discarding these two terms. So if we apply the rotating wave approximation, then the Hamiltonian of the interaction, and this approximation is very good for the majority of the systems that people treat in the actual lab, is H bar G of R, and now we simply have sigma A dagger plus sigma dagger A, which are the other two terms that we don't discard because they are the resonant terms, or the co-rotating terms they are called. Okay. Another approximation we will make is called the dipolar approximation. And the dipolar approximation, again, it was discussed already during the discussions on the semi-classical model. And the dipolar approximation is based on the fact that the atomic size, if we have the cavity with a wave inside, or something equivalent to it, and we have the atom here, the distance between the protons and the electrons, so the atomic distance, a whatever, a little circle, compared to the wavelength of this wave is very small, so lambda is much bigger than A0. But this means that in the place in which the interaction is happening, the electric field can be considered basically constant. So this means that the coupling constant, that in principle depends on R, under the dipolar approximation becomes an actual constant G that is the same, because f of R, if you want, this function is just a number, is whatever number it is. Okay, so under these two approximations, the rotating wave approximation and the dipolar approximations, that are very common sense approximations in the majority of the cases, the Hamiltonian of the system, but not in all the cases. We will see in this series cases in which this is not true, in particular the rotating wave approximation, and we will have to work our way out of the Jaynes Cummings model. But for now, under these approximations, the Hamiltonian of the interaction is simply h bar g sigma plus sigma dagger. Oh, sorry, I was writing it before. Sigma A dagger plus sigma dagger A is simply written like this, where again all the details about the specific atom, the specific interaction, and the specific cavity and light you are using is inside this G. And so then we can write the total Hamiltonian of our system as the Hamiltonian of our atom plus the Hamiltonian of our cavity plus the Hamiltonian of the interaction. And this is called the Jaynes Cummings Hamiltonian. And this is the Hamiltonian that we will consider in the rest, and that we will try to analyze and study. This is the Jaynes Cummings Hamiltonian. And this is the first part of this video, which was deriving this Hamiltonian, justifying its form, why it has the form that it has. Now for this video we will also see the dynamics of this Hamiltonian, and then for the next video we will see the eigenstates of this Hamiltonian, that is called the dressed states, that are states that are a mix between light and matter, and the spectrum of the Hamiltonian. And then afterwards we will see some applications in terms of preparing non-classical states of light, like Schrödinger cat states and some other states, and Bell states as well. Okay, so for now let's look at the dynamics of this system. And for this, for the dynamics, we will make a lot of use of the fact that we solved already the semi-classical problem, because the equations are going to be equivalent, so we won't actually need to solve the equations explicitly. But let's recall that in the semi-classical problem one can write the state as a certain probability amplitude times the ground state plus a certain probability amplitude for the excited state times the excited state. This is general. This means that G and E is a complete basis. You can always write a solution in this way, and all the time dependence is in the coefficients. And then we wrote the Schrödinger equation, and we got the two differential partial equations for the two coefficients. Now the situation is slightly different, but we can do exactly the same. So this we could do because the basis of our system is clearly ground state, excited state. Because our system quantum mechanically was only the two levels of the atom, because light was classical. Now light is not classical, but we can also define a basis because we know the eigenstates of the light field. And in particular, the basis is clearly the ground state tensor product with the number states. It's just saying that, okay, I'm in the ground state and the cavity has this number of photons. and the same with the excited state. And for short, these states here, they are denoted as just Gn and En. They mean exactly the same thing. So now we can also write any state of the coupled system as a superposition of all these states. But now we have an infinite number of states in the eigenbases, because there is an infinite number of Fock states, because n can be as large as you want. So this means that now we write that this is the sum over the number of photons, and then we have a coefficient Cgn, specifying the n, and then Gn plus the same coefficient En. Okay, so this we can do. And now what we can do is exactly the same thing, is calculate or write down the Schrödinger equation to get the equations that are an infinite family of equations for the coefficients C, G, or E of n. But now let's let's first write the Schrödinger equation. So the Schrödinger equation is partial with respect to t of phi, or psi in this case, I guess, is minus I over h bar. And now we will have the Hamiltonian, but the Hamiltonian of the Jaynes Cummings is the Hamiltonian of the atom plus the Hamiltonian of the field plus the Hamiltonian of the interaction, applied on the state C that we just wrote here. Okay, and one can actually do that, apply all this Hamiltonian to see to get the equations. But now let's look at it a little bit without actually doing the math. So the Hamiltonian of the atom and the Hamiltonian of the field, of course, their eigenstates are the G, E, N. These are eigenstates of the unperturbed Hamiltonian, clearly, because N diagonalizes the Hamiltonian of the light field, and G or E are the eigenstates of the Hamiltonian of the atom. So when we apply this Hamiltonian to this wave function, we are going to get coefficients Cgn or Cen. We are going to get diagonal coefficients if you want. And the Hamiltonian of the interaction is the one that is going to mix states between them. It's the one that is going to create the possibility to have transitions between states, between eigenstates. That's why it's the perturbation. But this Hamiltonian in particular has the specific form sigma a daga plus a daga sigma that we saw before. But this means that when we apply this to the eigenstates, to these eigenstates here, the only coupling that we are going to have, that is possible to have, is someone in which you create a photon and then you destroy an excitation, or the opposite. So if I have a state, let's say En arbitrary, the only coupled state that can have with this Hamiltonian is a state G n plus 1, and vice versa. If I have G n plus 1, this Hamiltonian would give me En. So this means that we will have a set of equations, an infinite set of equations, but if we fix n, if we fix the number of photons in the cavity, then we would have two equations for the coefficients C, E, n, and for the coefficients C, G, n plus 1. This you can convince yourself by literally doing the math and applying the Hamiltonian to the wave function and writing the solution to that, or writing the equation, the Schrödinger equation in these terms. But this form here means that if we write down the Jaynes Cummings Hamiltonian in matrix form, what we would have is a block diagonal Hamiltonian, and this is the reason why this Hamiltonian can be actually analytically diagonalized. So all these terms are zero, in the sense that in the Hamiltonian the only possibilities of couplings are these ones. So this means that if I, for example, here they will have a term that is the coefficient that goes between a coupling of E, let's say, n to G n plus 2. But in order to have this coupling, we would need a Hamiltonian that has a term sigma a daga squared. But we don't have this term. And I say this because sigma is going to reduce the excited state to the ground state, and a daga squared is going to create 2 photons in the cavity. We don't have this term, so this coefficient is actually 0. So all the coefficients that are not next to each other in the number of photons is going to disappear. And so that's why this is block diagonal. But this is very nice that this is block diagonal, because we can now diagonalize one of the subspaces fixing n, so n is going to be a parameter, and then we diagonalize the total Hamiltonian. And this is the basic idea of what we are going to do. But for now, I'm going to write down the differential equations that you would get for these coefficients, that you can get them applying just the Schrödinger equation. And then projecting the Schrödinger equation, but this we did it in the semi-classical model, so you can look at it if you want to know a little bit the details. Projecting the resulting equation into En or Gn plus 1. With the resulting equation, I mean that we take this equation, you actually write down the entire equation, and then you project into these 2 states, because these are the only 2 states that are going to be important. And then what we get is these 2 equations. If we project into the En, we get that the derivative with respect to time of Cen is equal to minus I omega 0 plus n times omega Cen minus I square root n plus 1 G Cg n plus 1. This square root sorry, this square root is coming from the fact that we are applying an a daga. So when we are applying a daga to n, we get a square root n plus 1 n. That's why I wrote the relationship before, because if you want to do it, you have to know how the annihilation and creation operators act on the Fock states, but they act in this way. Okay, and then similarly for the other coefficient, we have Cg n plus 1 is equal to minus I n plus 1 omega Cg n plus 1 minus I square root n plus 1 as well G C E n. And these are the 2 coupled differential equations that, fixing n, we can solve. But notice that if we define omega n to be twice G square root n plus 1, then this omega n is very, very similar to the omega that we define, that is called the Rabi frequency, in the semi-classical model. And if we substitute this into the equation, then we get exactly the same differential equations that we solved already in the semi-classical model. So we don't have to solve it. We can see, you can go back and see the videos in the previous videos in which we solved these equations. They are not really hard to solve, but in particular we can literally use the results. So just to be very explicit, fixing n, what we do actually have is, if we are in the resonant case, so the resonant case means that the detuning, which is omega minus omega 0, is equal to 0. So this means that the laser frequency, or the light in the cavity, the frequency of the light in the cavity, exactly coincides the atomic frequency. We are in the resonant case. Then we have what we call at the time the Rabi flopping. But then now, if we omega nt, now we call the Rabi oscillations. So this probability is 1, and this is pi, 2 pi, 3 pi, 4 pi, etc. It's exactly the same result as in the semi-classical model. But here the difference is that this probability is the probability of the atom to get excited and the cavity to have exactly m photons. So what is happening here is that we are fixing the number of photons, and what we see is that there is energy transfer between the atom. The atom gets excited by absorbing one single photon from these Fock states in which it's resonant, and then it re-emits it into the cavity field, and this does it periodically in these so-called Rabi oscillations. And then in the nearly resonant case, as in the semi-classical model, we have a similar behavior. Now delta, this detuning is not equal to 0, but is close, let's say, to the atomic transition. We discussed also why in the videos from before, why it should be close. And now if before we had these Rabi oscillations perfectly well seen, now we would have faster oscillations depending on the value of the detuning and with a smaller amplitude. And in particular, the new frequency in which this oscillates is this omega tilde, that is a square root the tuning square plus this omega n square. This depends on n now, and this is called the quantized generalized Rabi frequency, because the Rabi frequency was omega. Then omega tilde, we defined it in the semi-classical model as the generalized Rabi frequency because it's more general, it has a detuning inside as well. So if the detuning is 0, then the Rabi frequency and the generalized Rabi frequency, they coincide. But here is also in the quantum version, is the quantized generalized Rabi frequency. But the physics of the dynamics of the system is the same. But this is the particular case of the dynamics of this system when the state of the cavity is exactly a Fock state with a certain number n of photons. So it's exactly a Fock state. But this is typically not the case, right? Because a Fock state in itself is a state in which the number of photons in the cavity is completely defined. This state is actually very quantum, in the sense that if you plot or if you look at the Wigner function in phase space of this state, it has negative values, which means that there are quantum correlations in the state. It's a state that is hard to realize experimentally. What one has typically experimentally are coherent states, which are the states that comes from a laser. So one has typically a coherent state that is defined in this way. A coherent state is, in the Fock state basis, is the state that I'm writing here. I'm going to assume that you are all also familiar with the concept of coherent states. They are very well studied in quantum optics, and they are the states that are quasi-classical states. They are the quantum mechanical version of states that are closest to the classical state. But apart from details, well, they are defined as the eigen states of the annihilation operator of photons, and these are the states that typically one has in a cavity. So these states, we can actually compute what is the probability of having m photons given a certain coherent state alpha, and we can plot it as a function of n, of the number of photons, and then let's say we will get something like this. So this is 0 photons, 1 photon, 2 photons, 3 photons, 4 photons, etc. And these are the probabilities of finding this number of photons in the state alpha. This, for example, is a state alpha with mean value of number of photons, which is, by the way, equal to the square value of this alpha. of around, let's say, 1.3 or something like that. It should be something like that, maybe. And this is a typical state that one can actually find in a cavity. But now let's look at the mess that this means, because now, as I wrote to you here this. So now imagine that we make an atom interact with this state. So this state is composed with a lot of different Fock states, and each Fock state here with a certain number m and the atom in the excited state is going to oscillate with the number m plus 1 and the atom in G, where m is a certain number that is a certain number. Actually, inside this is a label. It's just a number of photons. Each substate is going to do that, and each of them with a different phase. Or in another way of looking at it is this frequency, this Rabi frequency, depends on the number of photons. So it depends on this m here. So this means that when you put all of them together, if this number of n is very high, then it's a clear mess. What is going to happen, in the sense that the total probability of the atom to be excited is going to be a contribution from the different probabilities, from the different waves, from the different oscillations, from the different Rabi oscillations of each of the atoms, of each of the Fock states, sorry. So each Fock state will contribute with a different frequency to these oscillations, giving rise to a very complicated dynamics for the population, for the entire population. So actually we can compute, and we will compute this type of numerically, we will solve this type of Jaynes Cummings models numerically further, in which I'm thinking in doing some tutorial of Qtip, which is a Python library in which you can solve exactly this type of problems, and it's used by researchers all around the world, and it's very powerful. But we will see about it in the future. I think that is gonna be fun to actually be able to calculate, and very powerful. But let's say that this is the probability basically of being in the excited state. Now, if I have a coherent state inside, what I do have, and what we will see, is having oscillations that are very rapidly, that they go away, they collapse, and then they start again. But the behavior of this is not regular. It's a very chaotic and irregular behavior. And here I'm writing a coherent state with mean number of photons of about, let's say, 10. But this is just a number, it's to give you a little guide. So we see the collapse and the revival of some oscillations. This is true that we see, but this behavior is chaotic and is quasi-periodic. Now, if we increase the number of photons, because these oscillations are actually due to a quantum interference effect, because the things that are interfering are the probability amplitudes of all the Fock states inside that is composing this coherent state. Now, if we increase the number, we still see the collapse and revival, but now they are more ordered. Let's say they do like this, then they go away, then they come back, but then they go away, then they come back, and then they go away, etc. And this effect is called, let's say that here I had an n of the order of 20, let's say, and this effect is simply called like this, called the collapse and revival of the atomic population. It's an interesting effect. In the limit that n is really large, is a very big number, in that case light, this coherent state, behaves almost as a classical field, and in this case one recovers the semi-classical solution that we found and the rabbit flopping. It's only when the number of photons is small that you can start seeing the bumpy structure of light, the individual quanta that is composing the light field, and then you start having this quantum interference effect. And this is what I wanted to tell about the dynamics of the system, and the video will stop here. I think this is a good place to stop. In the next, we will see what are the eigenstates of the coupled light matter system, and these are called the dress states. So thanks all for watching, and see you in the next video.